And I begin the presentation. I think that you see my screen.
Not yet.
Yes, no problem. So I begin by a scoop. T CrB didn't erupt before September 2024. So the shock, of course. Just in short, T CrB is a recurrent nova symbiotic system with two recorded outbursts in 1866 and 1946, thus with recurrence time of about 80 years, which means that the system hosts a very massive white dwarf between 1.2 and 1.4 solar masses. The hot component has low luminosity for a symbiotic system with a few tenths of solar luminosity, which means that it is an accretion-powered symbiotic. Some orbital variations are observed, which means that the red giant fills its Roche-Lobe. Moreover, flickering in essentially B, V, X, and also in emission lines are observed, which can be considered that an accretion disk and its boundary layer is in action. X-rays are very strong, probably from the boundary layer of between the disk and the white dwarf. And last, we observed low on high set. A very schematic view of the system with the white giant, M3, M4 subtype, and which transfers solar matter to the massive white dwarf through an accretion disk. The strong wind from the white giant produces a dense nebula around the system. About the size of the system, it is as an order of magnitude about 1 astronomical unit, so much larger than in the case of dwarf novae. Here's the dash historical light curve in during the 20th century, showing the outburst of 1946, which raised the level of about magnitude 2.5, preceded by a very high state during about one decenny, 10 years, but also before this very high state, some ways of the luminosity. The last thing is that after the nova outburst, second burst has been observed. Just a minute, I admit new people in the room. I come back on my screen.
Finally.
Good. And here is the light curve obtained by AVSO observers in B and V bands during the last 10 years, about. and showing that from 2015, we have had an increase of the luminosity in B and V band until, in fact, April 2023, followed by a return to quiescence. I insist, I do not detect what some people call a pre-eruption disk, but just a return to low state. The same like Earth, but according to the orbital phase, with in blue and red. Blue, long time ago, before the ice state, and in red and brown, the evolution of the luminosity according to the phase. The current cycle is in black. One can see the increase of the luminosity, but also the impact of the ellipsoidal variation of the light due to the red giant producing a double wave like in the cycle. From the comparison of the luminosity of T CrB during the last 10 years and what has been observed before the 1946 outburst, Bob Schiffer, essentially him, produced some predictions about the next nova outburst. The last one proposed that the outburst, the nova outburst, would happen before September 2024 at what sigma confidence. This is just comparison of the similarities of the light curve. So I have a first question to Steve. Are pre-outburst signals observed in novae? This is the debate. With more physical studies, some teams, especially Luna and his colleagues, proposed a much larger estimation of the outburst as seen in the graph. And this is really more physical because the estimation, in fact, they do, is based on an estimation of the accretion weight in the envelope of the white dwarf, which varies depending of the high and low states. Ilkiewicz, Mikołajewska, and al. Considers that the active phase are quasi-periodic and are not connected to the classical nova outburst. So we have very different opinions from professional teams about the prediction of the next nova outburst. So, new questions to Steve about the accretion weight, variations toward the white dwarf, and also the question of the critical mass and the pressure, which triggers the thermonuclear runaway of Norway.
Francois, there's one thing I would point out here, that there's only one genuinely repeating recurrent nova that we know of, and that's M31 2008-12A. You know, it's great, great name. This is a recurrent nova that literally blows every year to within plus or minus like a week.
Yeah.
Not a single other system is anywhere near that regular. And the more regular they are, the shorter the period, the shorter the interval between outbursts. So there's something deeply physical about what's going on the white dwarf that has absolutely nothing to do with the environment in which it's embedded. Now, I agree with the argument that these are quasi-periodic. To say they have nothing to do with the nova outbursts, though, I think is wrong, because they clearly are changes in the rate of supply, but how rapidly the object, the gainer, can eat this garbage is a different question than how quickly you supply it. I mean, anybody who has ever tried to get a 3-year-old to eat vegetables knows that you can pile them onto the plate, but the kid isn't necessarily going to eat.
Okay, that's clear. Thank you, Steve. I showed that there are variations in the dash historical light curve at in spectroscopy with, for instance, the equivalent width of H alpha. One can see that we have a succession of active phase and what can be called by, for instance, Munari, super active phase that we have recorded this last 10 years. Here, I don't know. So I have a proposal for all observers is to monitor the T CrB for about 80 years after the next nova event. This is exactly what AVSO observers did in photometry. And for instance, for SS Cygni, there has been monitoring of the dwarf novae for tens and tens of years. Before that, in the 30s, some theories about dwarf nova events used the observations of EVSO observers. In very short, the evolution of the spectrum during the ice state. In 2013, the spectrum of the nova showing the essentially the continuum of the red giant with faint Balmer lines, H alpha, H beta, and during the ice state, a significant increase of first the intensity of the emissions, but also an hardening of the emission spectrum with the appearance of helium-1, helium-2 lines, nitrogen-3. And we turn to quiescence since April 2030. We have monitored all this episode. Here I show it with the equivalent weights of H beta and helium-2. And question, Ilkiewicz, Mikolayevska in 2023 proposed that eventually it may be the result of, for the short active the active states outburst, or for the big active phase, a super outburst of the disk. We detected very precisely in April 2023 the end of the ice state, and the result has been published. And one important thing is that there has been no dust formation. Why do I say that? Because Bois-Schiffer had affirmed that this was the result of dust formation. Not at all. We can show that with our spectra. And in fact, in a recent Zoom conference in September, he admitted that thanks to amateur spectra, us, there is no dust formation. Now, the behavior of T CrB during the last year, here in 2023, there in 2024, with the end of the ice state, the variations, we have a hole. And for, of course, the next solar conjunction, we should have to reduce the gap. We note a very low state during several months. And the question I have to raise to Steve is, was the disk drained? And very accretion rate during this period. Well, for this year, here we have the orbital phase. We have an increase with not smooth, but we have an increase of the equivalent widths of the flux. Sorry, these are flux calibrated spectra. Mm-hmm. So the situation is very interesting because we don't know exactly what happens in a nova before its outburst. And whatever the date of the nova outburst will be, we collect very informative information. I am now in the idea of the lines formation in T CrB. They're showing some profiles from H alpha, helium 2 on 1 lines, showing various profiles for the same phase. And also O3, the forbidden line, with very narrow width, about 55 kilometers per second. For this one, this is clear that the line is formed in the nebula. For the other line, are those profiles, especially in Balmer lines and helium 1 lines, with often a double peaked, are the result of the emission from the accretion disk, such as we can see in other classes of objects, and or an extension of the nebula with self-absorption, in fact, of notably H1 and helium 1 line.
Francois?
Yeah.
Can I just share a screen for a minute?
Yeah. Or perhaps I have, I think, just one slide.
Okay.
So I propose I finish. This will be very quick, 1 minute, in fact. And after you have the screen. One can see also, according to the orbital phase, the variations of the profiles, and it meets the precedent question. Last thing, important for the subject of tonight, is the flickering observed in T CrB. Here's an example with luminosity in B band. which shows clearly from an autocorrelation spectrum real flickering and not variations due to noise and other. And a nice series obtained by our colleague Xavier Dupont, to resolution of 15,000, showing also sometimes, 2 times, clear flickering in the H-alpha line of T CrB. Here is what I had to say about as an introduction. And I give the micro to Steve. Steve, do you hear me?
Yes, this will just be very, very, very fast for the first part. I hope you can see this. These are model line profiles modulated by the orbit. In this case, we happen to have been here. We happen to have been modeling AG Drak, which is a symbiotic, but it's the same thing, that you have a single line profile that has here the absorption being formed by the column density in the wind, and that you simply have the wings because there's an H2 region around the accreting star, around the white dwarf, and that's being modulated by absorption through the wind and also shifting in velocity because of the orbit. So these profiles should be compared with these, which are the actual observations. And in this case, it's exactly the same thing. This is not an accretion disk. When you see this kind of double behavior, the width of the line, if it's excessively large, may be due to circulating material, but any flow that's in the vicinity of the white dwarf, because it's such a compact object, is going to show wings that go to a couple of 100 kilometers per second at full width zero intensity. So it doesn't necessarily mean that you have an accretion disk. I just thought this is much more consistent with what's actually happening in T CrB. And specifically, it's because as the white dwarf orbits within the background of the wind, it's accreting from the wind, it's illuminating the wind, so it has this ionized region that's trailing with it inside the red giant wind, which itself, I wasn't going to discuss that this time, but I should mention it, which itself is dynamical. That is, it isn't simply that, like a star in the center of the interstellar medium, where you form an ionized region around you because you have a sufficient ultraviolet that you can ionize the gas. It's not a stationary region. It's flowing. So you have the combination of the potential expansion of that region, but also the fact that you may have an atom that gets ionized by coming in the vicinity of the white dwarf and inside its ionization boundary. But then that just keeps going, and it may in fact recombine. So you have to be very careful to not think that when you're looking at a symbiotic, you're looking at something that's the analog of an H2 region. They're not the same thing. And unfortunately, this sometimes gets confused. You're spitting into the wind, actually. And any piece that gets ionized is also being advected, which also plays into some of what we can now go into if you'd like. So should I start? You tell me.
Yes, okay. Perfect. Thank you, Steve. Go on.
Okay. Trying not to be fastidious here. For once, I prepared some slides, but please, if I say anything that
Good.
isn't clear, just stop me, okay? So we have several different possibilities. Decretion is actually the polite way of saying what some in the business refer to as excretion disks. That is, to be less humorous, you have two possibilities when you have circulation around a compact star or even a normal main sequence star or something related to normal. Material can come in from the outside or it can leave from the inside. The leaving from the inside is actually something you're all living in. It's called the solar wind, which actually has a distinctly planar geometry, although the high velocity material leaves from the solar poles. You can think of the heliosphere as a kind of disk, except it's a ridiculously low mass. It's a very low density. You would never know it was there if you didn't throw comets into it periodically or astronauts. But it is nonetheless a disk which is controlled by magnetic fields on the sun, by the rotation of the sun, and confined to the plane of the ecliptic. In that sense, you can call it a decretion disk. It's not driven by radiation pressure. It's just evaporative. It's driven by the fact that the solar corona has a temperature of 1,000,000 degrees. The expulsion is the question that we're going to get to, and the everything in between is literally that you can see systems in which what appears to be an alternation between these different states occurs. So, okay, we talked about this last time, but I just thought I'd bring it back up. These are 3 recurrent novae. I just brought that up because it means we can intercompare outbursts, with the exception of T Pix. But LMC 1988 has a recurrence time of about 4 years. USCO is about 14 years. So one of these is closer to the fermentation of wine, while the other is closer to the optimum fermentation for cheese. And T Pix is kind of the other, which doesn't behave properly. It's a recurrent, but the recurrence time can vary by quite a bit. It's gone through 5 outbursts, but the last one was delayed by almost a factor of 2 in time interval. The reason I'm showing this is that the top curve is the X-rays as a function of time, and it's mostly the soft X-rays, which is the indication of the presence of the white dwarf. When you have an explosion from a nova, the material in the explosion is not homogeneous. You have internal collisions between individual fragments. So you get X-ray emission simply from the structure of the ejecta that has nothing at all to do with the underlying star. So you would never know anything about the accretion process from looking at the X-rays at this earliest stage, at the earliest few days. The second problem is you don't see the central object until the garbage around it, namely the ejecta, begin to clear. And In other words, the optical depth drops sufficiently. And that's what you're seeing as a perfect example in USCO, that the underlying source was on here, where my cursor is. You simply couldn't see it because in that particular orientation, whatever it is for the system, the ejecta were sufficiently opaque that they were absorbing all of the soft X-rays. It really doesn't take much column to do that. If you have an ejecta typical of classical novae, you can maintain that kind of optical depth for weeks. But once it finally clears, you see that there's also not a single nice, quiet nuclear engine burning. It actually is quite unstable, fluctuating by anywhere from tens of percent to factors of 2 on daily to weekly timescales. And these systems don't know what the hell a week is anyway, but it's a matter of the characteristic times. So there's one thing I should mention here because it's important for accretion disk and accretion processes. The typical oscillation time for an atmosphere on a white dwarf is a matter of seconds because the gravity is so high. These are 4 orders of magnitude as simple, either accreting or non-accreting white dwarfs. If they don't have something catastrophic that's gone on in their interiors, in their envelopes, they're going to have radii that are, about 1 Earth radius, and the typical densities are going to be about 4 orders of magnitude or higher relative to the center of a typical evolved star. 10 to the 8 grams per cubic centimeter is not unusual, and for a center of a hydrogen core burning star, it's going to be like 8 orders of magnitude lower than that. But the thing that's important is the surface gravity. I say that because that determines the mechanical structure of any layer that sits above it. That when we talk about accretion or we talk about structure, ultimately anything that's self-gravitating has its structure determined by the run of pressure in its interior. And that is a response to the way the layering above any stratum is constructed. So one of the things we're going to have to talk about is what that means. But once you know what the pressure gradient is, you also, in matter that's as dense as on a white dwarf, have one other piece of information. How, if you whack it, or if it hiccups, how will it oscillate? The characteristic frequency of the Earth's atmosphere is like tens of hertz. If Krakatoa or Mauna Loa blows and you get like the Tonga event, you get an acoustic wave that's traveling around the atmosphere. The frequency of that wave is in the hertz range or higher. On a white dwarf, the time scale is, oddly enough, about the same. And the critical rotation frequency is also about the same as the oscillation time. So it's just something to keep in mind. The other way you could think about it is, since the escape velocity is going to scale with the radius and mass of the star, the escape velocity from the sun is like 600 kilometers per second. From a white dwarf, it's an order of magnitude higher. So you would expect that if anything is circulating, it's also at some point, somewhere near the little bugger, it's going to be circulating with velocities of thousands of kilometers per second instead of what you have near the sun, which is more like hundreds of kilometers per second. Okay? So that's one of the other signatures that would tell you that there might be accretion going on. You would see the characteristic velocity of the inner portion of the flow. Okay, this was just, okay, so let me switch screens, hoping that this is actually going to work. Yeah. Okay. I'm hoping, Paul, that this actually works. Great. Otherwise, this is going to be another one of those cases of artificial intelligence winning. Well, here we go. Okay, rather than wasting your time, I will let the computer waste its time and kill this and go to another, go back here to another screen. So even if, okay, I really had wanted to do my own cartoons. I don't particularly like the way this is done, but it gives you the basic idea. First of all, let me outline one thing. Binary stars do not simply quietly cohabit. They periodically interact and do really nasty things to each other. And the thing that determines which one does what to whom depends on the mass ratio. That when you have two stars that have identical mass, of which I know only about 3 or 4 examples in the galaxy, under those circumstances, you might expect that you would be able to get these stars to somehow coordinate their evolution. But in general, we see that the mass ratio is not equal to 1. So since all stars start out with a stage of hydrogen core burning, their lifetimes are determined by the nuclear time scale to burn the hydrogen in their core, which scales with their mass. So leaving aside the mass luminosity relation and all this garbage, the higher the mass of the star, the shorter its main sequence lifetime. So if you start out with 2 stars that are simply a mass ratio slightly different than 1, the more massive star is immediately going to have an increase in its radius, necessarily an increase in radius over a time scale, which is the nuclear time scale, before the companion star winds up evolving. So the problem is they may start out with the same dress size, but one of them is going to be expanding faster than the other. And eventually, one of those, if they're close enough, is going to experience a serious tide. Now, leaving aside the exact shape here, the reason you get the distortion is simply because there's another object there that's massive. It doesn't matter how bloody massive it is. If it's the moon and the earth, then you're talking about changes of like 10 to the minus 4 or 5 in amplitude. If it's a star of similar mass, then the closer these things are, the greater the difference in the gravitational attraction from one side of the star to the other. Consequently, relative to the center of the star, these two appear to be pulling in opposite directions. It actually has to do with angular momentum also because it's a bound system, but I don't want to be confusing. It's enough to say that the shape of the star originally may be spherical, but you have a differential force relative to that that enters into the structure and that must be balanced by this pressure gradient. That's why I was talking about that. As the stars become closer in the sense that the difference across either one of them becomes large. They can either be close or one of the stars can be engorged or both. It's the fact that there's this difference. So if this star is evolving, it may start out without having any critical points on it and simply become progressively more distorted. But eventually, there may be, not will, but may be a point where it actually becomes so distended that the pressure is unbalanced. Now, this is a very important point, and I hope not too subtle. What happens is not that you get a point. This is a legal fiction that goes back to Lagrange. It's a so-called inner Lagrangian point. Lagrange was no more a point than this is. The importance of this is that it's a region in which the gravitational attraction of these two stars is approximately balanced. This is very important. If the gravity here, the local gravitational acceleration, is zero or damn near it, and it's of the order of what's called the pressure scale height, it's a characteristic length over which the pressure can equilibrate. So sort of the point at which when you're going up a mountain, your ears pop, that's about the point at which you've actually changed pressure significantly between the inside and outside of your ear. So it's about the same thing here. And exactly like your ears popping, the reason it does that is because there's a pressure difference. That on one side, you have the white dwarf. It has nothing around it, at least at this moment. And then on the other side, you have the equivalent of a balloon, which you've suddenly opened the snout of. And so you have an unbalanced pressure here, which forces material toward the other star. Literally, it sprays that material. And it sprays it at the sound speed because it is an unbalanced into vacuum flow. The thing that follows is that material isn't simply like the garden hose. It's falling into this other object. And because the system is in orbit, it is deviated and it circulates. And necessarily, that forms what we would loosely call an accretion disk, and it would be better to call it a disk-like structure. There is nothing that's going to force that material to accrete. I'll try to make that a little clearer, but the stream is narrowed for the same reason that when you open the tap in the kitchen, the stream that's coming out of your tap is narrowing. It's not that there's a pressure drop, it's that it's locally nearly incompressible, and the damn stuff has to fall through at constant rate of transport of mass. So as it's accelerating, the area decreases. The stream becomes, because of that, autocollimating. It's moving supersonically because it's literally falling. And it's deviated for the same reason that it would be in any rotating frame. That's the Coriolis, that it just doesn't fall directly toward the companion. And what's more important is the higher the velocity at the launch point, the more this deviates. So the stream is deviated. Some of it is just going to go off. This is very important to remember when you're thinking about the accretion process. It's not the nice, quiet, almost science fiction level pizza-like disk surrounding the white dwarf or any other star. It's a mess. The best way of putting it is accreting stars are messy eaters. And an awful lot of it just winds up being wasted, thrown out, blown off the plane, and blown out into the plane, because when this stream is deviated, even if it were to go perfectly around, when it collides with itself, there is a shock of enormous magnitude because this is a very, in the case of a nova or a cataclysmic, this is a very compact object. You have hundreds of kilometers per second difference between the velocities of these two streams, which is more than enough to require an insurance claim that this collision is going to heat the gas to at least a megakelvin. Now, that's going to be very quickly dissipated, but a standing shock of a couple of 100,000 degrees is perfectly possible, simply because any material that succeeds in circulating is necessarily going to slam into itself. And that's what basically sets up the disk. That's why I said it's a mess, that any deviation at all in this stream is going to change that shock. And the thing that's most important to remember about shocks is that you don't know they're coming. So the material that's circulating literally is not going to feel the presence of the stream until they collide, because the motions are so strongly supersonic. Now, this heating has two effects. One is to inflate the disk locally. So this is not planar. Keep this in mind, please. Accretion disks do not look like the rings of Saturn. They can't. That's a cold system. It isn't just that it's pieces of ice. It's that the random motions of those pieces of ice are extremely small relative to the orbital motion. So the planetary disks are going to be extremely thin. Essentially, they're as thick as the most massive, biggest boulder that happens to be circulating. The difference is here, you have heating from a kinetic process, and that's going to inflate the disk in the vertical direction, because that's the direction that's the least impeded by both gravity and angular momentum. This is on cylinders. So although we talk about thin disks, that's only an approximation. That makes an assumption about the way the heating and the cooling are going to occur. But overall, the mass exchange, if the systems are close enough, will depend only on the flow through what's called the L1 point, and from this structure, which is referred to as the Roche lobe. The term, I should also mention this then historically, calling this the Roche surface, or if you were doing planetary, it would be something like the Hill radius. They're all basically the same thing. It's a critical gravitational limit. The difference is that Roche was treating the problem of incompressible, meaning liquid, meaning constant density, which is really a better term, rotating bodies, and found that there was a critical shape to those. Then Darwin, the son, George Darwin, did one up on his father, and instead of dealing with the descent of man, dealt with the descent of the moon, and came up with the idea that you could have a tidal limit. So all of this, I mean, this basic picture could have been done 100 years ago, except for the critical point that they wouldn't have understood what was going on with the stream. Okay, I had to show this, that there's another possibility. If the stars actually are close enough, they can overlap, and so you get the equivalent of a scamorza. This is as close as I can come to showing you a common envelope. These are also called, on the main sequence, W Ursa Majora stars. Those are not the same thing that we're talking about in accretion. That's a flow, a common flow around the two stars that's bound to both of them. Again, it's messy, but it's more like a weather system than an actual hydrodynamic stream. It's in fact, very, very similar to what happens in the Earth's atmosphere. So it's because here the two stars are close enough together that they literally sit inside an atmosphere that's co-circulating. Okay, so the other signature was what Francois was showing in the recent observations, and this was one I just pulled up to include because it shows the behavior over just a 2-hour period. Flickering is another example of this messy behavior, that it's noise, it's bubbling, it's vortices that are colliding and shearing within the disk. When you talk about accretion in a binary system, it's enough to say that it must take place in a disk. Whether that disk is stationary or not is a totally separate question. And I really want, if there's nothing else you come away with, I really want you to come away with that concept, that the reason it's a disk is because there's angular momentum in the system. That defines a plane. And the material, when it's launched, is launched like the nozzle of a balloon toward the companion at very low velocity. It's essentially leaving at the sound speed. And so it falls in, and the way it falls in is in a planar trajectory. So what you start out with, if you could imagine this thing starting clean, would be an environment around this very compact central object, which had the material just blowing onto it. If you do this in a wind, it's the same thing, just not as efficient. That it's very, very important to remember that, let me see if, that when you have a wind blowing past a compact object, as you do in a symbiotic, that wind is still like the solar wind, carrying angular momentum. The central star, sorry, the companion star is rotating. It may not be rotating synchronously, but it can't not rotate because it's feeling a tide, and that tide is stirring the little bugger up. So when material is flowing in that system, it already has some deviation. And so it's going to carry more of that onto the companion. Even if there's the slightest accretion, it's going to show flickering. It's that simple. There's nothing profound about it. Accretion occurs on the surface of an object that's embedded in a medium whose velocity is supersonic, period. So let's go to the next slide. This is not deliberately complicated. This just happens to be one symbiotic system, RT crucis. The importance, okay, this is the flickering. The only thing, the takeaway here, the only thing you need to look at to really understand is this thing in the upper left-hand corner. That's the power spectrum, not the periodogram of this flickering, that shows that it's just featureless and extended as a power law. This is a characteristic of noise. And it's also the characteristic of turbulence. That there's no characteristic scale means that whatever you have is a dynamical process that is occurring on many different length scales and many different time scales simultaneously, which means turbulence. So it's not something that's nice and well ordered. If you're interested in the accretion process in any system, this is the first thing to go for. If you, as a side comment, decide you're going to use a periodogram to do an analysis, as opposed to what Francois was showing, which is an autocorrelation, which is directly related to this. If you use anything that looks for a period, you'll find one. You'll find lots of them. Very densely spaced, and depending on your sampling window, potentially looking as if they're really pulsation periods. When you say quasi-periodic, it just means there's a characteristic time scale, and if it's really flickering, there isn't. This is an old example, but this is looking down onto and across the accretion onto a white dwarf in a wind. This is actually a model for RS-Ophiuchi, but it could just as easily be T CrB, that you have a wind blowing from a red giant companion, which is off to the side, and that material, some of it, you see how messy it is here. This is the side view. At a distance, this is the close-up. You get a thick region formed, but that's still clearly planar. You have structure within that are spiral shocks because of the way the accretion is occurring. It's going to show jets and streamers, but all of this is because the material that's deviating here is shocking itself and forming the disk. This is what T CrB, I think, looks like now. That you wouldn't want to be standing next to it, okay? But you can see that clearly something is going on, and whatever is modulating this disk is what we have to talk about now. I hope this is making sense. If it isn't, please stop me, because since I can't do the cartoons, even though I had checked it out beforehand, I have to rely on your imagination and whatever word power I have. The other possibility is the accretion onto a magnetic field. In general, we try to avoid mentioning such things because magnetic fields and pornography have the same role in society and astrophysics, but it's inevitable because compact objects have intense magnetic fields, even if they only had very weak or just remnant fields from their earlier lifetime. White dwarfs can have fields that are easily above a megagauss. Now, to put that in perspective, that's about 1,000 times more than the strongest sunspot fields, which are exceedingly localized on the sun. Normal stars, or even abnormal stars in their ordinary evolution, don't develop surface fields that are above about 10 kilogauss. So you're dealing with something here that's strong enough and material that's ionized around the star, susceptible enough that the magnetic field can actually control the behavior of the accretion process. Now, to put this in perspective, so let me stop screen sharing for a moment and do something like video. So can you see my hands? Yes? Like, so
No.
can let me stop sharing then. Okay, can you now see me?
Yeah.
Okay, so I'm going to have to do this the really primitive way, which is like Disney cartooning. So this is an accreting white dwarf with a magnetic field. Okay, The first thing is this region out here is the accretion disk or the accreting environment. The part in here is the region like around the Earth that is the stellar magnetosphere. It's the region in which the magnetic field controls the flow of the material. In exactly the way that in the Earth, we have a magnetosphere because there's a finite density to the environment of the Earth, and the lower part is controlled by the magnetic field out to some critical point where, because it's rotating, and also because we have material falling in, there's an equilibrium balanced surface, which is called the magnetopause, in exactly the way that it is for the magnetic field of the Earth and the solar wind. Okay? There's no difference. Well, there is in density, but that's about all. That if we look at what's going on here, and we keep the material circulating, there isn't some magical wall that stops the accretion because you have the magnetic field and it just slams into like a brick barrier. It's that the material here in stopping is also going to be heated, and it's going to rise and follow the magnetic field lines. I'm sure that you've all seen pictures of sunspots in, say, H-alpha or in the ultraviolet, where you see material above the spot in arcs that rain down onto the photosphere and the chromosphere. So you have an arc that begins cooling and the material moves on an arc. It doesn't just drop. It's clearly constrained by something. That something is the magnetic field. What we're seeing in the magnetic accretion, in an accretion disk, is precisely the same thing, just in the opposite direction. The heating is in the disk, and the material is then forced onto the pole because the pole sits on the star. So instead of falling straight down, it falls along this arc. How it does that is what I was sort of showing in the illustration from Romanova, that, as you can guess, this is a hard problem. These are old calculations, but they're very illustrative, that material is heated here because of the interaction at the disk, and then it falls down in the same way that in the solar corona, you get coronal rain. The difference being that in that case, it's a static arc, and here it's rotating. And so this becomes a kind of curtain. Hence the phrase that I think was introduced by Brian Warner, or Brian Gensick, the accretion curtain. But the key point for understanding it is that the point at which this boundary of the magnetosphere occurs depends on simply the outward pressure gradient of the magnetic field and the inward force of the accreting material. So it's a dynamical balance. On the one side, you've got the material falling in, and on the other side, you have, because it's ionized, the equivalent of a wall, strings that this thing's going to have to get through. So the standard picture of what this all comes to is this. This is the standard cartoon of SS433, which is a microquasar. It's a fairly massive black hole, stellar mass black hole with an accretion disk that precesses with a period of about 160 odd days. It has a jet that's moving at like a quarter the speed of light. It's the poster child for how we're going to understand an active galactic nucleus, but it's just an accretion disk. It just happens that the thing at the center is a black hole, which is precisely what I'm not going to talk about. They're too simple. I had to say that, okay? That the impression that one gets is that because you have to use a theory of gravity, general relativity, to understand what's actually happening in the inner part of the accretion disk of a black hole, that somehow this is a harder problem than the ordinary problem of putting a white dwarf or a neutron star in the center of the same accretion flow and asking what's going to happen. You have the advantage in a black hole that it's a black hole. That's not being funny. Um, when you fall in, you keep falling. And when you fall in, you don't stop suddenly and feed back into the material that's coming in. You just keep going. That's the fundamental difference. When I said that there were X-rays as the indication of the white dwarf, the reason you can say that is that is the requirement that this material is falling onto an extended object and it has to come to rest. And if you fall into a black hole, you don't even have to radiate. You can fall in so quickly that the material can, in fact, not radiate because it can't cool, because it can't collide in the time locally in its own frame that it takes to fall through the event horizon. So the phenomena associated with the accretion onto a black hole are much more energetic because the gravitational field is so much stronger in the inner disk that you see phenomena that are in the 10 to the 9 Kelvin range, even higher than the 10 to the 5 or 10 to the 6th. But on the other hand, you'll see non-thermal processes, but many of the thermal processes you won't see. So just to show that this is what happens when you take a shear flow, a compressible flow, and you put it through a background gas. On the left, it's a straw stuck into a tea kettle. On the right, it's an industrial level smokestack. I didn't fake these pictures. These really are as close as that. The difference is the one on the left is 1 meter long and the one on the right is about 15 meters long. And you see, this is what's meant by self-similar. These are the same flow. They're subsonic. The ejection velocity is actually probably damn close to similar. The material that's coming out of the nozzle is almost invisible because it hasn't yet accumulated material from the environment. That's why I'm showing this. In fact, the original project, the one on the left, was to study that process. It's called entrainment, that the flow here has a different velocity relative to the background. It's more easily seen with a jet than it is in planar flow. And because of that, material is swept up in vortices into this flow. And because it's expanding, it condenses, it's aerosol, and you see it in scattered light. And you can see the vortices along the edge. Now, which means that if you were to take, and this isn't unrelated, if you were to take a cut here and just look at the way the flow, say, passes this point, you'd see that. You'd see flickering. Now, this is going to be the rest of our discussion, centered really on this. We have an advantage in Novi, in the modern era, thanks to many of you, that what had normally been a flash in the pan, and still is for a lot of people, that the only thing that much of the community cares about is what kind of transient they're seeing. And after they know, they stop following it because it's boring. Fortunately, there are people like all of you who get interested in these things and keep following. So since we know that systems like USCO and T CrB and T-PIX and RSO are recurrent, somehow the accretion has to restart. The last time we talked about how novae are accumulated material leading to an explosion, sort of like what happens in a corn silo, where you build up to a critical layer, a critical level of temperature and pressure, and then the thing explodes. It's a little more complicated than that, but who cares? The point is, you build a layer at some rate that has a finite temperature because of this background pressure. And eventually, it may reach the critical threshold to trigger a thermonuclear explosion. However that happens, and whatever is the subsequent behavior, from the classical nova point of view, the thing that's important is that after the explosion, this object is damaged goods. The white dwarf is not the same as it was while it was accreting. Francois used the word quiescence. I'm not sure what quiescence means when you have an accretion disk. It would be better to say it's kind of minimal state because it flops around. That's what you're seeing here. But once the explosion has occurred, and it takes a finite time for the system to relax, the other object, the other star in the system, couldn't give a damn that its companion has just gone through a cardiac. It just starts dumping. In fact, it was continuing to dump even during the damned explosion. It's not suddenly that you've got to keep this in mind. This is not a kitchen sink. It isn't that some super being comes along, and once that creature sees that one of the stars is about to explode, it turns the faucet off. And then once the material has blown off, it turns the faucet back on. The companion star, depending on its evolutionary state, is going to suffer the consequences of that explosion, not necessarily the dynamical, because nova envelopes are pretty damn trivial. They're 10 to the -5 or 10 to the -4 solar masses. So it's like blowing Jupiter at the sun. Okay? On the other hand, in fact, it's pretty damn close to that. On the other hand, what remains is this very hot object that is cooling off because for a while, the super soft source tells you there's a nuclear source there, and you're seeing it. Remember, I said that the beginning of that phase is because the material is opaque. So the fact that you're seeing the soft source means that whatever material is now circulating around it, and it's inevitable that there is, must be optically thin. Or if it's not optically thin, then it's at least thin enough that you can actually see the central object. Eventually, the central object is going to turn off. But that may be for a variety of reasons, not simply that you've exhausted the nuclear fuel. And that's where this flickering comes back in, that the process of accretion is going to produce flickering. And so even if it's flickering for a very simple reason, you have stuff that's falling onto the white dwarf. It's getting heated, and it's ordinary gas. The material is falling on us, not degenerate. Now, the other signature that you might have re-accretion has always been said for this system, and always meaning like the last 30 years, to be the shape of the light curve, which is this. that you see an eclipse, that around the white dwarf, what people have called an accretion disk has reestablished. I'd like to argue in explanation that that's bunk. It is not a stationary disk. I said it must be disk-like, it must be equatorial, but it's going to be bloated and with an interior object that doesn't look right. Difficulty we have with the recurrent novae, and I'm going to emphasize this for the rest of the discussion, is that they challenge our understanding of what happens in the accretion process. If you've got an ordinary nova, the typical picture, the picture we have is that after an explosion, it kind of sits around for a couple of millennia and then accumulates material, but the garbage is coming onto the pile slowly. And it takes, 10 to the 4 years to build up to the critical state, and then it blows again. This is referred to as hibernation. But it's very easy, if you take that scenario, to imagine what's going on. The white dwarf, during the explosion, blows off its envelope. It recovers, but it recovers on a time scale of maybe a decade. Well, if you've got a millennium, who cares if it takes a decade to come back to its minimal state? Okay? But if it takes a decade and the bugger blows every 10 years, it never reaches a minimum state, and we don't know what that looks like. When you do the modeling, you start with a white dwarf and a companion, you throw material onto it, and you see what happens. Okay? In other words, you imagine that this thing is starting from scratch. This is garbage. We don't see that. What we see is something that's had a history that we don't know. We just meet, it's two strangers that meet on the street of the galaxy, that we don't know its history and it doesn't know that we are watching. So we're seeing it in one of these cycles. We have no idea what it looked like when it started, but what we do know is how it behaves from cycle to cycle, if it's recurrent. And if it's not recurrent, we don't know that. So instead of saying this is what must be happening, I'm going to say this is the challenge. How does the system relax? And what does that do to the accretion process? Again, because the companion doesn't give a damn what's happened. The companion is always throwing mass out through that inner point. It can't stop because it's a star. Okay? So this is what a disk looks like. This is a protostellar disk, but it's the same thing. That this is a classic image from a long time ago, and I'm showing it precisely because it's old, that you have a central star here that's accreting, central protostar, and because this is a tilted disk, this is the bright reflected light from the inner part of the disk. But you could look at this as being what this disk in USCO looks like. That you've got the white dwarf here, and you've got this garbage around it. And yeah, it has a disk-like shape, and it has a characteristic structure. This happens to be self-gravitating, which is why you see this kind of bagel shape to the object. But nonetheless, it's not thin, it's not flat, and it's going to take a long time for that to relax. Now, some text. How do you get the matter to the disk? And then how do you get the matter through the disk? So we've got the matter to the disk with no problem. That's literally falling off a log. How you get it through the disk? That's a problem. Because You got to think of this as a ring. In the simplest case, you would, in fact, form a circulating structure, but it's very difficult to get material to move radially in a gravitational field once it has angular momentum. If you can stop its orbit, no problem, it falls. You know that because you can return to Earth from the ISS. Okay? All you got to do is get the angular momentum dissipated and poof, you're on the surface. That's the problem. It's really easy if you're water, and it's really hard if you're a gas. The best example of an accretion flow, a bathtub. Never mind the central vortex. That's just the demonstration that there's actually a finite thickness layer here. The point is you've opened the hole and material is falling down the hole because there's nothing to stop it. It's a continuous medium. It's viscous. Okay? This is the thing about water. Feynman talked as a wonderful joke about dry water, that you would take a shower and it would be like feeling something hitting your skin and running over it, but you'd still be dirty. The reason water sticks is because it's viscous. Never mind whether it's surface tension or internal friction, it doesn't matter. It's viscous. There's a characteristic scale over which material in this bathtub is coupled on a time scale. If you move stuff here over some time scale, there's an expanding region around that line that feels the effect of that drift. That means that eventually the tub will empty. That's also because this is really gooey stuff. In an accretion disk around a white dwarf, for example, the densities are something like 15 orders of magnitude lower than you're seeing here. And the velocities are something like 10 to the 8 times faster. Okay? That is thousands of kilometers per second instead of centimeters per second. And in terms of the viscosity, it's incomparable. As a result, you would think that the material should be viscous because it should be turbulent, which in other words is that. Okay? That if you have a shear, a difference in velocity that's large enough, it should generate some kind of a turbulence. That's what you're seeing here. To give a side comment that I hope won't be too boring. When dealing with the origin of turbulent flows, it isn't simply fluctuations. Something much more than that. You're transferring momentum and energy. You're getting the stuff to move, and you're also getting dissipation. Getting it to move depends on the differences in the velocity, the shear. The dissipation depends on the viscosity, and it's a balance between these two that determines whether you actually have turbulent flows or not. The greater the shear, the greater the difference across the smallest region, the greater the propensity to turn turbulent. This is the fundamental axiom, the core axiom of turbulence theory. It's also the bane of our existence because we don't really know why that works. But it's enough to say, I hope, that it's always going to be the presence of shears and twists and turns and all of the chaos that you're used to seeing when you look at clouds. Now, That works really well if you've got a jet. It doesn't work here because there's something going on here. And I'll get to that in just a second, but this is an example of what I mean by shear. These are pictures of the Arno from a few years ago, like 5 years ago, where the central channel here, this is near my house, is was moving at something like 5 meters per second. And the material, the water along the banks was essentially stationary. And so you could see that there was a shear flow between these, which looked like this. On the right-hand side, you have essentially stagnant water. On the left-hand side, you can see from the streak lines that you have moving fluid, and then this is the layer between them where you go from static to co-moving. This is a boundary layer. And you see that it's, again, a mess. That if you have a shear flow, and this is the simplest form of shear, it's horizontal, so gravity plays no role in this, incompressible, so you don't have to worry about shocks, you don't have the characteristic sound speed. On the left side, the material is flowing straight through, and on the right-hand side, it's stagnant, and there's a transition region between the two of those. Okay, this is the classic example of a boundary layer. The next is in the atmosphere. The top is a shear flow, and you can see the vortices. This is actually a stratified flow on a scale of something like 10 kilometers. And the bottom is a boundary layer, also a shear flow, except you don't see the thing that's driving it. Okay? It's just wind. That's that simple, that because you have flow over the surface, you have a pressure fluctuation, the surface begins to deform, and the difference is this is vertical. The other one was horizontal. So you're lifting material, and it has a characteristic fall time. This is called a gravity wave, not a gravitational wave. That you're taking the material and raising it up. And this is why I said at the beginning, there's a typical time scale for a white dwarf of seconds. That's the oscillation time for this wave if this were on a white dwarf. You'd have the shear flow of the disk around it, and the surface of the white dwarf could ripple like this. I say like, okay? Not that it will do this, but this is a way of visualizing it. And it will turn turbulent, it will break, and it will be very complicated, exactly the way this is. Okay, this is over Dulles Airport, and this is Liguria. They couldn't be different, more different. This is incompressible. This is totally compressible. Okay? The next difference is this is neither of them. This nor the Arno is an example of a rotating shear flow. And that's what makes accretion disks much harder. That here and here, you have gravity or not, but you don't have angular momentum. This is an example from Marco Bellomo's thesis where you have a shear flow in an accretion disk. The lower material is a white dwarf, and the upper material is the boundary layer of the accretion disk. And you see, it looks a lot like the Ligurian beach, that you actually do get breaking waves, and you get little vortices, and you get big vortices. And if you let this go on long enough, it does this. It mixes, okay? Like this, without the seagull. And in fact, if you look at the really extreme case here of very high shear, this is actually much more than the one that was forming the ribbons and little dimples. You actually see this, that the layer lifts up and it's mixing these two together. These only are temporarily coherent. If you leave them for long enough, they're going to mix. This is the accretion process. This, people, is flickering. Okay? This calculation doesn't include the thermodynamics and the radiative transfer simultaneously. So you don't have, in the current models, the actual flickering as a product of this kind of turbulence, but it will be there. And the characteristic timescales will be seconds to minutes. It's the consequence of having the material up here moving differently than the material down here. Now, a demonstration of that was from last year. This is the most dramatic example I've ever been able to photograph from the ground. You see the dark layer here? I hope.
Yes.
This is not this. Okay, that there's this line between the two regions. Okay? This lower part is an aerosol pollution-dominated layer over Pisa. This was not a good day. The upper part doesn't have that at all. And the contrast between those two is the condensation point. This air was completely mixed with the lower part. This air is not. And there's literally a stratification between those. That is what the white dwarf should look like if it weren't accreting. On the other hand, I knew from that day, because looking toward the other direction, there was a shear flow. So it hadn't hit this layer yet. This was an advancing front. But you can see what the mixing looked like. It's simply illuminated differently by the sun. But this upper layer is actually this layer. It's just because I happen to be inside of it. And here it was looking more horizontally. Here it was looking more vertically. Okay? That's what you would see if you were standing on the white dwarf. The final example of a shear boundary layer, which is the best I've ever been able to photograph. This was 9 years ago over the Atlantic. Over the Irish Sea. The lower layer is at about 5 kilometers, and the upper, the plane at this point was at like 11 kilometers altitude. So these waves are just the result of a shear. Again, it's the generation of vorticity, but there is a characteristic time scale here which is connected with gravity. It's just not strong enough to produce mixing. So, the signatures. The way you can tell that you got an accretion disk is first that you've got a binary, and then that you have emission lines. This is a trailed spectrum, a portion of a trailed spectrum of an old nova. V1369 Sen was Nova Sen 2013. And these spectra were taken around 2019. So this is the time in hours over which the sequence is seen. So this is a really short period object. Okay, these are the calcium H and K lines. Those are interstellar. This is a helium line that sits on top of the H line. And you see that there are two features here, an S wave and a kind of blob. This is a hydrogen line. This is a hydrogen line. They don't look quite the same in the variation as the helium. This is a whole sequence. It's not the best slide in the world shown this way, but each one of these is that same interval Each one is tracing a different line. This happens to be from the ejecta. That's why it's not varying. Okay? All of these others are indications that material is following one of the stars, orbiting with the same amplitude as that star is, and broadened relative to what you would expect if it were just material at a particular radius. That's the signature of an accretion disk. Not that it's a double peak profile, not that it is a stationary structure that gets, sliced and diced in the eclipse, but that it follows one of the stars, and the width of the line at any phase is consistent with orbital motion. That is, it's consistent with what you would expect for the size of the disk, the size of this critical region, and the circulation velocities of that material. And this is the model. Just to show that, yeah, if you've got an accretion disk and you have a hot spot and you got the disk and we have the hot spot here that is at a different phase, and yeah, you can reproduce it. There's no big deal. Okay? Yeah. What also indicates that you've got a disk, and I'm really sorry for not being able to draw more cartoons here, is that the material can be, the gas that's coming in from the companion can be dumped onto the white dwarf so quickly that it piles up in the disk. You can think of this as a clogged drain, that you're trying to get the white dwarf to accrete faster than it can hydrostatically adjust to. Now, to explain this one point, the gas that's coming in has to settle on the white dwarf. That's why I was talking about the boundary layer, and I haven't talked at all about the viscosity in the disk or anything like that. Just the thing that's really important for understanding what goes on in a nova is not what the viscosity in the disk is. It's that material somehow gets through the disk. We know that has to happen, so that's a different question now. We can actually cheat. What we want to know is, how does it get onto the white dwarf and mix? Because that's where you're supplying the fuel that's going to cause the explosion. That inner part is completely dominated by the reaction of the outer layers of the white dwarf, independent of the disk. If the white dwarf, because the material, when it falls, has to stop, hope that the importance of that statement sinks in. You have gas that's coming in at hundreds of kilometers per second that has to somehow come to rest, or else it ain't going to accumulate on the star. Some of it is going to blow off because it's slamming into the surface and being compressed. But if it can cool, then it can accumulate. It won't build up a reaction pressure gradient. But if it can't cool, then it piles up because the material is consistently coming in from the disk. Because this is supersonic, the disk doesn't care about what's going on the surface of the star any more than the companion cares about what's going on in the disk in supplying the material in the system. So inevitably, the disk is going to inflate, it's going to become opaque, and it's dissipative. So The mid-plane is like a hot plate, and the surface is space. So it starts to convect. And in convecting, it behaves locally just like a Cepheid variable. It starts pulsating. And welcome to an example, SS Cygni. This is what dwarf novae do. They vertically pulsate. They cycle between these states of engorged because of the mass exchange rate and quiet. In fact, this is entirely on the disk. This has nothing to do with the white dwarf itself. But this wouldn't happen if you could just throw the material directly into the white dwarf. So you will not see this behavior from black holes. You might see it from neutron stars, but you'll definitely see it from white dwarfs. This disk instability is just thermal. It is not nuclear. And it's related to the flickering, that when you have this disk instability, you will see the flickering, but its frequency will change because it's coming from a different part of the disk. Okay? So, stop sharing now for a moment. The other side of this, I do have to be honest about, is understanding why the material falls in the first place. Not from the L1 point, but why is it coming through the disk? We can cheat and say that there's some kind of a turbulence. So the same thing that happens when you flush a toilet, that you get enough shear and you get bubbles and local coupling, and the gas would behave like the water in suddenly turning strongly coupled over many scales. And so we would call that viscosity. It's just that it's circulating. And that's what makes this a hard problem. You see, if you're orbiting, that orbit, if it's a two-body orbit, is stable. The only way you can move in is by slowing down. By slowing down, you go to a closer orbit, which means your orbital speed goes up. Okay, this is the apparent anomaly of gravity. It's attractive, damn it. So you fall in faster if you lose angular momentum. So if you can slow something down in its orbit, it will drift inward. And the faster you slow it, that's a terrible phrase, the more efficiently you slow it, the more rapid the drift will be. Okay? That works great if you play magic. That is, you put in something that you call turbulence, you have no idea where it came from, but turbulence isn't something that just happens. You have to generate it, and you've got to maintain it. And if you have a shear like the Arno, you saw it, you could do that. If the shear gets large enough, you inevitably get vortices, and you get bubbles, and you get filaments, and you get coupling. Okay? You get turbulence. If it's orbiting, you don't do that. It's stable. And that has been the core problem since accretion disks were recognized 50 years ago, that we know what the behavior has to be. We know what the magnitude of the coupling has to be. But if it were just what you see in the bathtub, it wouldn't work. You need something orders of magnitude more efficient than anything that you're going to have from kinetic effects. We just don't know precisely how to do that. The best argument is that these are disks, these are ionized disks, and so they have currents, and because of the shear in the currents, you can actually generate magnetic fields locally. They don't have to be more than very, very weak dynamos. And that actually provides some strong coupling because you start shearing that and it reacts. There's a tension that is created that behaves precisely like a viscosity. At the moment, that's the best solution that has come down the pike. It's been around now for a little over 30 years. It's one of those features in theoretical astrophysics that we know what we know what the process has to look like. We just don't know exactly how to generate it. And it is very much something that does not happen at the level of the laboratory. We're not dealing with the hydrodynamics of a bathtub. But overall, the thing to keep in mind with accretion is one, it's inevitable in binaries. Two, accretion is inevitable and the formation of disk-like structures is inevitable whenever there is a shear present. So if you've got a white dwarf, for example, that's accreting from a background medium, if there's any asymmetry at all in the density distribution, you're going to get a disk. If there's a wind, then you have to get a disk because the wind in an orbital motion always carries angular momentum, and so on and so on. The final point being that the opposite side, namely decretion, can occur if, for any reason, the central object is spinning faster than the material is circulating around it. See, the assumption here is that in the accretion process, in the boundary layer and in the inner disk, the underlying star is just passively sitting there and going, feed me, where it might actually be like, for those who know Bugs Bunny cartoons, like the Tasmanian devil, that it could be spinning much faster than the inner disk. It is possible to do that, in which case the exact opposite process will occur. You'll get a centrifugal wind that the inner region may, in fact, cause, by viscosity, an outflow of the background material. The way this would happen is if you had a very wide binary and you have a very inflated star. So it's got a long moment arm and it gets spun up. There's a class of stars for which this has been suggested. They're called B bracket E stars. The BE stars may very well be partly this mechanism, at least they're thought to be. One of the difficulties with the BE stars is you have a normal star, not a white dwarf, that's surrounded by a disk, but the disk is extremely optically thin and also unstable, and maybe fed by a binary, and maybe internal, and maybe both, which is why I said, and everything in between. The BE stars are a much, much more complicated problem than the cataclysmics, in my opinion, because they are so marginal, and there are so damn many of them, and the objects that are accreting are so big and fuzzy and normal. That's the hard part. I'll just make one last comment here as I hope a poetic thing to think about. It's very easy to imagine wind flowing over an ocean and generating waves because you have a very, very rigid surface. So you understand something about this very sharp contrast. But it's the same process as winds blowing through a cornfield or a wheat field or over grass. Because there's a pliancy in the surface and there's a characteristic response time because of the elasticity. In all of those cases, they're either, that's very close to a white dwarf. They're either horizontal or vertical shears, but they're very similar to having a wall. When you have something like algol, the accretion is more like blowing air over a bunny. It's kind of soft and fuzzy, and it pulsates and it reacts on timescales that are longer than the circulation time. And that's hard. We don't know how to solve that problem yet. It's fully three-dimensional. And the last of all is what I think is the most challenging problem facing this field. And that's what a common envelope does. That is, in astrophysics, one of the core problems that's remained from the beginning of the 20th century. We know that in binary systems with periods of a day that are about the mass of the sun, instead of having an accretion disk, mass is simply flowing between the two stars. That's why I showed the Scamorza. We don't know how that works. That's been a problem since literally my childhood. And because it doesn't seem all that sexy, has remained sort of on the periphery of binary stars for at least a generation. It is now absolutely vital, because that's what happens in the last stages of stellar mergers. That's what leads to cataclysmics. That's what they evolve into. So the common envelope, the circulation without accretion, with material being blown off in winds and carrying away energy, kinetic energy and binding energy from the system, is the next step. We can study the physical process when looking at cataclysmics and looking at algol-type systems, but then the final challenge is what happens in these extremely dynamical stages. Again, I apologize for not being able to cartoon, but I hope this has made sense. I'll shut up now and hope that you're willing to raise points. So thank you.
Thank you very much, Steve.
Thank you, Steve.
So I have a problem with Steve. I have one question, and from his answer, I have 10 more questions.
Okay.
Terrible. Thanks a lot. Guys, if you want, you can take the micro and share your questions with Steve. Do not hesitate.
Like, please.
Any question? And,
What are you, all Midwesterners? I had 10 years in Indiana, and whenever you wanted to control the behavior of first-year undergraduates, the thing you needed to say was, "Does anybody have a question?" It was beautiful. After that, you could hear a pin drop.
Steve, I have a question.
Please, please, please.
If you go to this Lagrange point and you say it's not a point, it's more like a nozzle.
Yeah.
And what factors would determine the diameter, I guess, of that nozzle?
That's why I said it's about a scale height. It's the distance over which you could have a sound wave establishing constant pressure, which means it's only a tiny fraction of the radius of the star, but it's about the same as a stratum of the atmosphere. So it was the example when I said that's why your ears pop, that it can't be much larger than that, because you have material that has on one side no balancing counterforce, that it's simply being drawn toward the other star. The key point about the theoretical or the abstraction of the L1 point is that it's the point in space where the gravitational acceleration is zero in this co-rotating frame. But it's not at the center of mass. So when material is forced through that, it also deviates. Okay, it has angular momentum at that point. And so it's already flowing kind of in a cant. And again, that takes place within this region in which the pressure can sort of adjust to a constant value. It's really a very, very small fraction of the radius of the star. So in calculations, it's treated as a point. But it's actually very close to what you would have known from Boeing as a nozzle. It's actually very similar to a de Laval nozzle in its basic behavior. In fact, it can't be a point because the gas isn't at zero density. You don't have a single particle going through. You see, when you look at the shape of the Roche surface and you say these are the Lagrangian points, the reason for that is those are surfaces on which you have constant potential. Or put it another way, in the old celestial mechanics literature, they were called surfaces of zero velocity, that something could just slide on those surfaces and it would feel on that surface as if it were a surface, that it's a pressure surface. But it's not a single particle that you're sending through the L1 point at any moment. It's a stream. And the stream isn't coming out at zero energy. It's not coming out cold. It's hot gas. It's coming from the interior of the star. So it's going to be spreading even as it's approaching that point. It doesn't simply fall directly as if it's single particles. And that's why I said it's about one scale height and size. Okay?
Thank you. Any other question?
Yeah, Steve, I've got a question. On that inflow, assuming both objects have magnetic fields, is the assumption that you're in the locked-in phase where the plasma is locked in with the magnetic lines, or is it more of a free flow? I guess it depends on the plasma beta, right?
You said it beautifully. It's that the gas doesn't have to be completely ionized. It's simply that you have a neutral fraction and an ionized fraction. And it's the same particle just spending its life in two different states. So every now and then, it may recombine and it may like jump to another region of the field. That doesn't matter. Overall, the gas behaves as if it's tied to the magnetic field. And so, yeah, precisely. It behaves like a fluid that has threads going through it, which are the magnetic field lines. If, like in a protostellar system, there are portions in the outer region where the densities are very low, but the temperatures are also low, it's entirely possible that those regions are going to be able to slip through the field. Okay, so actually, I think, yes, a miracle just occurred. I'm going to take advantage of this miracle situation right now. Okay, so you can see that there's actually a whiteboard, right?
Yeah.
Okay, so what's actually happening in that case is that the inner region here is where you have the magnetopause, and the disk is sort of out here. okay, where this is being dragged around, okay, so the disk is actually circulating here. And if you were to look at this from above, you would have the central object, you'd have this inner boundary region, and you'd also have these shocks, like all through, simply because the velocity isn't steady. And the magnetic field then couples through these, and the material is heated here because it's slamming into this now stopped material and literally forced up the poles. And because I now have the ability to do the cartooning, let me go back to one point in answer to the previous question, that this is what you mean by having the Lagrangian point here. If you expand this, it looks like this. That the star here isn't a single point. This is the region that's like perhaps a few thousand kilometers on something that's a solar radius. For all practical purposes, that's a point. But this is the region in which the pressure in the interior is greater than zero, and the pressure out here is approximately zero. And so what you get is here this flow through that would fall directly to the companion if the companion were simply stationary, but it's coming out here with a deviation, a total some additional angular momentum. And so it deviates and then slams into itself. And this is where you get the hotspot formed. Okay, so the region here is determined by the gravitational potential alone and the fact that it's coming out of an extended hydrostatic object. This region, the magnetosphere, is where the outward magnetic pressure is balancing the inward dynamical pressure of the accreting flow. And that's exactly the same thing we see in the solar wind. That is the outer boundary of the magnetosphere. This is effectively a magnetopause. It's exactly the same thing that happens when a CME, coronal mass ejection, passes the Earth, gets trapped in the magnetic field and funneled toward the poles, and you get the auroral display because of the auroral ring in the inclined magnetic field. Where life gets hard in this problem is that if you had this, you as an observer would never know that there was a magnetic field there. You would simply see the emission, the X-ray emission from this magnetosphere, but you'd have no way, except maybe for the flickering frequency, of knowing that this thing was a magnetosphere. Instead, the way you know it is because if the field is inclined, then the material is going to accumulate at the poles asymmetrically. And that's called a polar. And there are novae that are polars, and we do our best not to talk about them because it's one of those cases where the buildup of material is here at the poles. It's not over the whole surface of the star, which is the implication in the way I described it. It's not even just in the equatorial region. It's only at the poles. And here, it's even at the poles over a different time scale, because this is actually creating a kind of sheet of accretion, where here, it's actually a donut. It's a very different dynamical problem. But at large distance, it's the same, that it's simply that the disk is ionized. The application of this coupling was first developed for cataclysmics because the central object is a white dwarf. And so the material that's falling in and whatever shear is generated is going to give you temperatures that are enough to ionize hydrogen.
Do you see jets
Okay.
on the poles?
What you actually see at the pole is an X-ray pulse that it looks like a pulsar, except it's in X-rays. The way you know that it's actually a magnetic pole is by polarization of the lines that are formed in that region. So the hydrogen lines are actually polarized by the Zeeman effect. They show a circular polarization. And that also tells you that the magnetic fields are like 1 to 10 megagauss, which we already knew for some white dwarfs anyway that aren't accreting, because you can measure the quadratic Zeeman effect and know that the white dwarfs, when you can see the hydrogen lines, actually show the effect of the extremely strong fields on just ordinary non-accreting white dwarfs. But what you see is a time variation. And in the X-rays, for example, one of the novae that I showed, Nova LMC 1968, has a 300-second period. And that's clearly the rotation of the white dwarf. More than that, the pulses aren't well enough defined to know what's going on. But you see, this is why if you have a rotating star, if there's even a very slight magnetic field, it's going to impose a period on the flickering. And if you do a power spectrum, you'll be able to get that out. Again, even if there's no magnetic field, the white dwarf is rotating. It's not stationary. So there's a characteristic frequency there. Make it slightly magnetic, even with very weak magnetic fields, but not necessarily, not dipole. Okay? And you're going to see this wealth of fluctuations at the surface, at the boundary layer. We see this also in accreting protostars. So they're already the test bed for this. In effect, what's going on cataclysmics is a lot easier because it's in such a high temperature regime that you know something about the heating and cooling. It's the cool stars that are actually hard. But I hope that helps.
Yes. Any other question? Seems that no. So thank you very much, Steve, again. And tomorrow I will send you the link to the video, of course. And we can.
Oh, one thing, please. I just realized I forgot to show this. The best example of a white dwarf in a boundary layer
No problem.
that I'll show you. Okay, everybody ready for this? This gets to be a movie. Can you see this?
Yeah.
There it is.
Mm.
There's your boundary layer. Okay. Okay, fine. So it's not exactly a white dwarf, but it's white and it's rotating. And there's an accretion stream. And in fact, the reason the damn thing is rotating is because of the accretion stream. This is in Carrara. It's one of the fountains, and I think it should be a pilgrimage spot for astrophysicists. that there's the boundary layer. This is what viscosity means. This is the same thing that happens on your tires when you go through the rain, that there's a separation level here, but at the beginning, this is following the surface because of the viscous flow. And then the separation is occurring here because of the pressure gradients. So So that's
yeah. Nice. Okay. Thank you very much again, Steve. I think that it is very appreciated. You lost only 5 attendees. Congratulations.
They must have eaten early. So, well, thanks very much. It's always
No, very
very
thank you
moving.
very much.
So
Fantastic. Okay, guys. So I think
bonsoir,
that
bonne nuit. Dormite bene. Okay.
so goodbye and see you soon, guys.
Yeah. Thank you very much.
Thanks a lot.
Goodbye. Thank you, Steve.
Thank you very much, Steve. Bye, everyone.
Thank you, Steve. Good night.
Good night, all.
Ciao, Steve.
Good night.
Thank you. Good night.
Okay. I'll sign off now, Francois. And merci bien.
Thank you. Thank you so much.